we present our research work, Safe On-Orbit Dislodging of Deployable Structures via Robust Adaptive MPC. Safely dislodging underpowered solar panel with a hybrid hinge has become increasingly significant in space operations. As solar panels are critical for powering spacecraft, any malfunction or deployment failure can jeopardize entire missions. Addressing these issues is crucial for maintaining the functionality and longevity of space assets, ensuring the success of various space missions. In this background, the adaptive control or MPC method became popular in aerospace servicing and repairing tasks, focusing on parameter estimation and precise manipulation in the past decades. However, first, considering most of the state-of-the-art adaptive control methods, including the decentralized adaptive control method from our previous work, the parameter estimation at the end of the manipulation task is bounded so that it's hard for the controller to get the true value of the parameters of the unknown manipulated object. Second, most adaptive MPC research in parameter estimation only focuses on the time-invariant parameter system, which assumes the estimated parameters are constant values. Considering the unpredictable space environment, this limits the servicing and repairing missions in space. Third, parameter estimation accuracy in most of the state-of-the-art adaptive MPC research works is so insufficient that it is challenging to meet the requirements of highly accurate control of dislodging task, let alone the unpredictable time-varying parameter system in space. Fourth, the performance of the accurate manipulation task, especially dislodging in space, depends on the balance between the exploration in parameter estimation and the exploitation in control actions under the unpredictable environment and limited knowledge of the manipulated object. In this work, we develop a novel, robust adaptive MPC algorithm, as shown on the right-hand side, and implement it in the space dislodging task under the limited knowledge of the solar panel with a hybrid hinge on a space station. We define a free-flying space tug installed with a robot arm that can apply 6 degrees of freedom wrench in 3D space to finish the dexterous manipulation task as our servicer, and the solar panel with a hybrid hinge which is jammed and underpowered installed on a space station as the client. Here, first, we build up the dynamics model of the client within the Euler-Lagrange model. Then, to design our robust adaptive MPC algorithm efficiently, we transform the equation into a state space model. We assume our manipulated object is a time-varying system in which we have 3 time-varying parameters, k, zeta, and dk, to denote the time-varying properties of the client, including stiffness of the hybrid hinge and the grasping information of the servicer under unpredictable space environment. The update rule for the parameter estimator is shown on the right-hand side. For the MPC block, it contains a prediction model and optimizer. The predicted state tube in the estimate is shown on the right-hand side for the prediction model. We minimize both n one-time steps for the cost function and consider the terminal set with the following constraints. We introduce upsilon in our cost function, which is our main contribution to improving parameter estimation accuracy during the dislodging manipulation. The right-hand side shows our algorithm in detail to fully introduce how our algorithm works and how it balances the exploration and deportation during the dislodging manipulation task and parameter estimation at the same time. We then implement our method in the MuJoCo simulation platform, an advanced physical simulation platform that can simulate a zero-gravity environment like space. Our servicer contains 1 free-flying space tug with 6 DUF in red with 6 thrusters to support its motion dynamics and 1 robot arm. Once the solar panel is out of the safe range, as shown in the green region, the color will turn to twinkling, and once the control input from the robot arm is out of its safe range, its color will turn to red. Here, we choose 2 baseline methods for the comparison. For PID, it's very easy to make both state and control input out of their safe range, which can endanger the whole system. The state and control input results during the dislodging task on the right-hand side prove that. We can also see that the adaptive control method makes it easy to put the solar panel and robot arm out of their safe range during the dislodging task. In the end, we can also see that our robust adaptive MPC method can protect both the solar panel and robot arm in their safe range during the dislodging task. The results on the right-hand side clearly show the safe constraints we set for the robust adaptive MPC well for both state and control input updates. Then, to show the advantages of our algorithm in parameter estimation, we chose a state-of-the-art adaptive MPC method and adaptive control as two baselines for comparison in parameter estimation. For the adaptive control method, the 3 time-varying estimated parameters update versus time shown in column A. Then, for the compared adaptive MPC algorithm, the 3 time-varying estimated parameter update versus time shown in column B. In the end, we implement our robust adaptive MPC method, and the results show in column C. Overall, when we compare all methods together, it's straightforward to see that our algorithm performs better for the parameter estimation in both speed and accuracy compared with the other two. We also prove the feasibility of our method in hardware experiments, considering the limitation of our testbed. Here, we choose the time-invariant parameter system as our target manipulated object. We leverage our testbed that uses the UR5E to emulate the servicer to dislodge the solar panel with a hybrid hinge, and use the WAM robot installed our satellite module to emulate the client. In our experiment, we assume the dynamics decoupling between the satellite and space servicer can proceed during the whole process of the dislodging task, which means the WAM robot will decouple the dynamics from the solar panel when the solar panel is dislodged by the UR5E. In that case, the satellite is always relatively static with the world frame in our testbed. First, we choose the PID as the first baseline for comparison. It appears that the PID method makes it very easy to make the whole system out of the safe ranges, as the red dashed line shows on the right-hand side, including what we set up for the service manipulator. Also, the angle and velocity of the hinge are very easy to get out of its safe range. Then we implement our adaptive control method as the second baseline. It appears that even though the adaptive control shows better than PID for its accuracy and stability, it's also easy to be out of the safe range for both the manipulator and manipulated object. In the end, we implement our robust adaptive MPC method. The results on the right-hand side show that our MPC method shows very good performance for both control input from the manipulator and the state status of the solar panel. Without being out of the safe range, the whole system can be safe during the dislodging process. Thanks for watching.